this is your setup. You have this circuit here connected to a power supply that supplies power to the circuit this way. You have a volt sensor connected to capstone on either side of this. You'll build your circuit off of these springs here with these alligator clips. You'll have a switch here that you can open and close the circuit. And then you have a wireless ammeter here which connects up to capstone. We'll do that in a moment. You then also have a light bulb. And then you have three different ceramic resistors. All four of these are what you're going to be doing, what you're going to be characterizing in part one. You want to figure out what the resistance is of each of these as you increase voltage and measure the current that is passing through each of those. And to do that, you'll first need to characterize each of the resistors with one of these multimeters. One of the multimeters is going to be set up to measure both voltage as well as resistance, and the other multimeter with the wires diagonal to each other will be set up to measure current in the milliamp range based on the unit shown shown right next to the port. This one will be in milliamps. You will be measuring direct current, but that's going to be in part 2 and part 3 for series and parallel circuits. So in the meantime, you first want to start characterizing your different resistors by taking the ohm meter setting, switch to ohms. Note that there will be different units depending on what type of resistor you're viewing. Right? If there's infinite resistance, it shows mega ohms. If there's basically no resistance, it goes down to showing just ohms, because mega ohms is going to be a much higher resistance. But what you do is you take the alligator clips, connect it up to the resistor, and you'll see in this case, I'm reading 127.3 ohms is the actual value for resistance of this given resistor. You'll do that for each resistor as well as the light bulb. Treat those as your actual values to compare your experimental data to later on. Then, back to the main circuit, we could take the resistor in part 1. As we characterize each individual resistor, we hook it up to the circuit with the alligator clips right here, as so. And then, what we can do is we can connect into capstone our wireless current sensor. There is a button on the back of it. As we press it, it'll flash light and it'll start blinking, saying, hey, we can connect it to Bluetooth on capstone. So if we go over here, we see in hardware setup, there's a little Bluetooth selector. Make sure that the number of the current sensor lines up with the serialized number on your actual sensor. You can click it, it will connect. You will now have both the voltage sensor as well as the current sensor currently connected up. So you can close that tab, and if we were to press preview, we'll see that those sensors are continuously polling, but we'll need to zero the sensors out because, as we can see right here, is not currently overlapping with 0 in current and 0 in voltage. To do so, we go down to the bottom. While it's in preview mode, we can select the different sensors with this drop-down menu. We can go over to this button here and press 0, and we've seen that we've moved the voltage now to the 0 line. And then we can switch to the current sensor, and we press 0, and now the current is also zeroed out. So the sensors are all good. All of that is done with this switch open to make sure that there's no current, no voltage on the circuit. We can at this point turn our power supply on, and we'll be measuring the current going through each of the resistors as you go from the range of 0.1 volts all the way up to 6 volts. 0.1 is going to be your low end. Then from half a volt up to 6 volts, you're just going to be doing that in half volt increments. That's all summarized on the back board. The process for setting up capstone and taking data is going to be up on the front board, as well as some notes for how to set up the multimeters if the wires have been removed. So back to capstone. What we see is with the circuit open, there's no voltage. As soon as we close the circuit, we'll see as we bump up the voltage of the of the power supply, we can see voltage in the voltmeter section, and we see some current in the ammeter section of capstone here. And if we were to press keep sample, then it keeps that sample in this data table down here, and you'll do that over the entire range of voltages. And once you've done the entire 0.1 to 6 volt range, you can go ahead and press stop at that point. Don't press stop beforehand, just so that you keep all of your data in one data table, all nice and collected. But now you have all your data that you can then go and copy, just manually copy into Excel and make your plots of voltage as a function of current, from which you should be able to derive the resistance of this resistor, as well as your other resistors, as well as the light bulb. And then compare those values that you get from your plots to the quote-unquote actual values that you got from your ohm meter here, right? And then something that you can do, if the plot gets out of whack, just to be able to see it in capstone, you can come up to the top left of the plot, press this button, it'll automatically scale the axes, and you can just see the line that you've created with this data set. That's pretty much part one, right? Part two, you will make sure to set the power supply to 4 volts, and you can double check that when pressing preview in capstone. You can either use the same page that you were on, or go to the second tab up here at the top to get a nice big voltmeter. We can see we're basically at about 4 volts. Get as close as you can. It doesn't have to be exactly precise, but basically 4 volts, right? And then, as the capstone is going, we can open the circuit back up so we don't get shocked. We can then go to our building out our series circuits as well as our parallel circuits. The series circuits will be where all the resistors are in line with each other. The parallel circuit will effectively make kind of a ladder shape where power is supplied to one side of each resistor, and then goes to the negative terminal on the other side of those resistors. And so what we can do to build out our series circuit, we just take our alligator clips, connect to one end of the resistor, connect to the other end of the other resistors. We now have, once we close the circuit, once we close the switch here, we'll have power going through all resistors. And at this point, the multimeters, both multimeters come back into play, where we want to use, where we want to measure DC voltage, right? DC voltage, the V with the dots and line over top, as well as DC current, the A with the line and 3 dots over top. That is going across, that's going across each of these resistors in this circuit, right? To measure the voltage for each, the voltage drop across each resistor, you can take your voltmeter, and when the circuit is closed, we're getting 4 volts through this whole circuit. We can just take our alligator clips attached to the voltmeter, go on either side of the resistor. We'll see in this case we're getting about 3.0 volts, or 3.04 volts. We go to the next resistor. This one's showing about 0.461 volts. This one, this last one, right? To measure the voltage drop, we want to be in parallel with said resistor. We're now getting about a half volt. So about a half a volt plus 3 volts is about that 4 volt voltage that we're supplying the circuit. You do this, you then can characterize the current that is flowing through the resistors by essentially becoming one in the series of the circuit. So essentially, you take your ammeter, right, the wires that are diagonal to each other, connect into the circuit. Open it just so we don't get shocked. Connect into the circuit. We are now part of the series circuit. We close the switch. We'll see, in this case, 4.29 milliamps, because we're hooked up to the milliamp circuit. 4.29 milliamps is the amount of current that's flowing through each of these resistors, because any current that has to go from one side has to reach the other side. And if they're all connected in line with each other, it has to go through this resistor, and this resistor. And so then you can just connect your ammeter one time to get the current that's flowing through these for the series circuit. It's a little flipped when you go to the parallel circuit. Same type of thing. You characterize the current and resistance, the current and the voltage going across each of these resistors, and determine what the overall equivalent resistance is for this entire circuit based on the 3 resistors here, and compare what you experimentally determine to be the total resistance of this circuit to the expected value based on your actual resistances that you measured way back with the ohm meter at the beginning of your lab, right? For the parallel circuit, to measure the voltage, again, you want it to be in parallel with the different resistors, right? Using the correct voltmeter. We go parallel to each circuit, or to each resistor. We see that we're getting, when we close the circuit, we're getting a voltage drop of 4.03 volts. At this resistor, we're getting a voltage drop of 3.9, if I make a good connection, volts. And we go to the third resistor, 3.5, if I can make a proper connection. It should be roughly 4 volts. So long as everything's connected, it should reach about 4 volts. Basically, every resistor in the parallel circuit, all of the charge is built up on one side, has to get to the other side. There's the same amount of potential difference between one side to the other side. So the voltage in this case should be the same, but current not necessarily, right? Because now you have 3 different resistors. The total amount of current needs to go from one side to the other, but they have 3 different paths to go through depending on how resistant, how constricting each resistor is. And to measure the current, again, we want to become part of the series of these resistors. So in this case, in the middle one, you can think of it again as a ladder. We've become this rung of the ladder to measure how much current comes through this resistor to the ammeter, back to the other side, and so on. You do that for both the series and parallel circuits, characterize the total equivalent resistance of each of these circuits, compare that to the theoretical expected value based on your actual resistances that you measure with the ohm meter, and that's the end of lab. I think that's pretty much everything. Again, this is all done at 4 volts. A warning to state is whenever you are using, we'll just take it from here. Whenever you're trying to use the ammeter, the one with the diagonal values, the one that's going through a fused circuit inside, the one that's trying to figure out how much current is going through the circuit, make sure that if you're using it, you are going in series with a resistor, as so. In this case, I am letting the current pass through this resistor, pass through the ammeter here, and back to the rest of the circuit. If there was no resistor, right, it's as if we have a swimming pool that we're trying to drain out with a hose. The resistor, in this case, would be the equivalent of the hose that's draining the pool out. If we instead, I'm not going to do it with the circuit open, or I'm going to do it with the switch open. If we're to instead just take the wire and go like this, it's as if we're slashing the pool open and all that water comes out really, really fast. The electrical equivalent is all of a sudden there's a effectively infinite amount of current going through, and it's going to burn out the fuse in here, and it could damage other bits of the circuit. So always make sure that there is a resistor in the series whenever you're trying to figure out how much current is flowing through something. In this case, through this one resistor, we're getting 30 milliamps. Cool. That note is again up on the front board. Notes, other notes on the front board is how to connect the wireless sensor up to capstone. and then the entire lab is summarized again on the back board. For your plots, for your voltage versus current plots, there is you can use the linest function there in the bottom back right corner of the board to determine the slope of your plot as well as the uncertainty in the slope of your plot. If you plot voltage versus current, well, voltage divided by current should equal resistance. So the slope should be your resistance. And if you get an uncertainty of that slope, there you have an uncertainty of your resistance. That should be everything now. Okay. Good luck.